Welcome everyone, my name is Nicolas Valenzuela and today I'm going to present a research work that I'm doing with my supervisor and Yale University. A topic of my talk is stochastic detection of malwares using API trace similarity. So let's get started. As I mentioned before, this is a joint research work which was done together with the Yale University of South Korea and the Federico Santa Maria Technical University in Chile, both recognized for their work and professionals in the field of the engineering. So, having already mentioned this, I will tell you how the presentation is divided. We'll begin with an introduction of the topic to explain some basic concepts and tools for the development of the paper. Later, we'll go to the core of our presentation, where we'll show the proposed method and an empirical analysis of the work done, to finally conclude our work. First of all, to contextualize us, what is a malware? A malware is a piece of malicious code that allows us to perform unwanted actions on some system. Recent malwares, however, has been created intelligently and in an uncontrolled size, so that current detection methods are no longer sufficient. Methods based in signatures, for example. This paper and presentation propose an efficient dynamic malware detection method based on API traces similarity, proposing to overcome the traditional signature method. So, we talk of API or Application Program Interface to the set of libraries that use a system to work with the different characteristics of this one. So, we focus on dynamic analysis of API call traces, string machine distance, and assign score until obtain the result. According to AV-TEST, there are over 390,000 new malicious programs detected every day. Therefore, malware detection and analysis is considered being one of the most important fields of information security. As you can see in this graph, the amount of malwares by year increased rapidly, as well as the difference of malwares made for Windows and other operating systems is enormous, surpassing by more than 70% the amount of malware made for Windows in the current year. So, let's go for some interesting things about the malware analysis. When we talk about malware analysis, there are three main techniques that help us to understand the behavior inside a system and how a malware interacts with the different characteristics. We have static detection first, where we extract malicious information from the malware before it's executed. For example, by analyzing the assembly code of the binary file and understanding the API calls that it's made to the system. Unlike the dynamic detection, which is an analysis done after the execution of malicious program. This is done by monitoring system calls or monitoring new processes that are created, for example. Finally, we have the hybrid detection, which is responsible for operating in both contexts. Then we have the Levenstein's algorithm, which gives us the minimum number of operations, either insertion, deletions, or substitutions to transform a string into another. For example, if we have the word C and we want to take it to SIF, we must replace the A with the B. Therefore, the distance of Levenstein is a measure of the similarity between words, and in the context of malware will help us to find the similarities in some characteristics extracted from the malware. In this section, we present a method based on API traces similarity for dynamic malware detection. The generated malwares scored by the proposed method are used to measure similarity between different datasets. The workflow consists of 6 parts before obtaining the final result. We will explain each of these blocks in the following slides. The first step is through the use of dynamic analysis of malware to collect different API sequences traces of malware execution, which will be part of the dataset that will be used in the following steps. After, in API filtration, the repeat called and parameters are filtered from the previous information in order to have a set of different strokes from each other, allowing us that data is not redundant. At this point, each malware will create a family of patterns that will represent a modified version of the original malware. These modifications refer to the number of observed APIs. For example, the first pattern obtained may contain 120 API calls, while the second 225 API calls, and so on. These patterns often arise when packers are used to alter the code, so the number of patterns will depend on the number of API calls made by each package file. Then we'll define AX as the test file, PX as the pattern to compare, and the sum API as the total number of API calls observed. We'll say that a match with a registered database pattern is found if the following conditions are true. The first condition is if the sum of the API calls from the test file is greater than or equal to 85% of the sums of the API calls of the parent to be compared. And in the second condition, alpha must be fulfilled, being the equation above or my condition. If this is true, it's assumed that the sum of the API calls of the test file is equal to the sum of the API calls of the parent to be compared. Otherwise, we'll say that no matches have been found. So, however, a successful match doesn't mean that the test file is similar to the malware pattern. The API similarity algorithm is calculated later to determine the similarity score. Now, in group initialization, we create groups for the filtered API call sequence for both AX and PX. Each one contains 4 equal groups, as you can see. For example, the G group contains load library, resume thread, and other DLLs of the API call sequence. Later, after obtaining the groups, we'll construct the malware feature, represented by the letter F. This will be done by concatenating the API call sequence of a particular G group, obtaining the malware feature that you can see on the slide. So, the table below illustrates the characteristics of test file and compare malware pattern file, with the corresponding scores, which will be explained in the next slide. Finally, we reach the final step of our method. This is the heart of the research. The trace similarity algorithm that allow us to calculate score and distance of all features. This algorithm summarizes the parts mentioned above by adding the calculation of the scores. In particular, we need 2 strings to find the distance between them. So, as you can see in the center of the algorithm, we have a loop, an iteration for each feature, and calculate the distance for every feature string f of malware mn to the corresponding feature string of malware m. So, while comparing the features of the dataset, if the size of feature f is larger than feature f of m, then we trade off the overflow characters. Otherwise, if feature f is less than the size of feature f of m, then we fill the missing API calls with null values. Finally, the score is calculated by finding the sum of the mini scores, and now we can generate some results about this. So, in this section, we will explain the tools used, the data collected, and the results of our experiments. Let's start with some tools used. First, we have the next generation virus creation kit allow us to generate viruses which are automatically morphed. Several techniques are used to morph the viruses, such as random functions order, anti-debuggers, junk code, etc. Also, we use a Flux Trojan and a remote admin tool, RAT, a client-server architecture where the attacker can use Flux clients to generate the Trojan or servers. Flux use advanced techniques to evade malware detection and firewall, such as encryption and code injection methods. As you can see, we generate 100 Trojans with Flux and another 97 malwares with Next Generation Virus Creation Kit tool. That is 197 malware in total, in addition to using 50 benign files for the test obtained from Softpedia and included in software of Windows 7. To extract API calls, we use Sandboxy Analyzer with BSA program and database patterns are selected by taking random samples of the generate malware families. Thus, for this experiment, Flux have two patterns, pure and morphed, while NGVCK have only one pattern, and the implementation was code in C++. As you can see, figure 3, 4, and 5 show a plot for dataset scores, where red line is malicious samples and blue line are benign files. From these figures, we can see that a threshold is established and is consistently able to distinguish between benign and malicious samples. For this part, we use the Reciever operator curve or ROC. This is used for selecting classifiers based on their performance and to calculate the area under the ROC, which is a portion of the area of a unit square, with value between 0 and 1. This index can be interpreted as the probability that a classifier will sort or score randomly, choosing positive instance that is higher than a negative one. We use them as a measurement of success for the proposed method. So, the scores for both Flux Pure and NGVCK malware are better than the scores of Flux Morphed malware, while it is clear that the proposed method is effective in detecting package malware. We can see that the proposed method achieves high accuracy of detection, and it would also help in detecting zero-day malwares, since the API's call traces for malicious files can sometimes have the same behavior. Finally, we can say that current malware detection techniques are not effective enough for the number of threats that are born day by day, so it's imperative to improve our detection techniques. The proposed methods offer the possibility of detecting malwares effectively, using arbitrary similarity in dynamic analysis, and the implementation thereof show promising results. As for future work, data mining classifiers such as KNN to classify score can be used to quantify malware and benign files, and in addition, we could apply our method to be engaged in static analysis and collect the opcode sequence instead of API calls. Thank you for watching and have a nice day.